Hey everyone, this is Dr. Walker. In this video, we're going to look at two examples from video 8C on the graphical interpretation of velocity. Let's look at the first example. We are given a position time graph. Remember, the position is on the y-axis and the time is on the x-axis. And we're asked several questions about finding average velocity and also instantaneous velocity. So, what we learned in video 8C is that to find the average velocity, which is defined as delta x over delta t, we just have to find the slope of the line joining the 2 points. So we're looking for the average velocity from the 0 to 4-second time interval, from 0 here to point A here. So we need the slope, which is the rise, which is the delta x, over the run, which is the change in time. So that's the slope is going to be 2. We're going up 2 meters. And then over, we're going 4 seconds. So that means that the average velocity is 0.5 meters per second. And we're just going to leave that as a positive number, implying that the motion is to the right. Part B says, what is the average velocity during the 8-second to 12-second time interval? So I encourage you to try it yourself and pause the video. We're going to do it the same way. We're going to find the slope of the line joining the 2 points from 8 to 12 seconds. So the slope is going to be the delta x, and we're going from 10 down to 0. So delta x is negative 10. And then divided by the time. The time is from 8 to 12, which is 4 seconds. So that means that the average velocity from 8 seconds to 12 seconds is negative 2.5 meters per second. As we see, this is a negative velocity because we're traveling from 10 meters down to 0 meters. So that is a velocity to the left. Now part C says, what is the instantaneous velocity at point A? Do you remember how to do that? We said in the video that to find the instantaneous velocity at a point, you have to find the slope of the line tangent to that point. Remember that instantaneous velocity is defined as the derivative of x with respect to t. So point A is right here along this straight line. We have already found the slope of this straight line. So a line tangent to this point would be a line that is parallel to this straight line. So we already know the slope of that line. That's what we found in part A. So that's 0.5 meters per second. So whenever you have a constant velocity, such as from 0 to this point right here, that means that any instant in between those times, you're always going to have an instantaneous velocity that is equal to that constant velocity. Let's look at the last part. What is the instantaneous velocity at point B? See if you can figure this one out. This one is a little bit tricky. Remember, we have to find the derivative at that point. The problem is that this is a sharp point, and the derivative is not defined at a sharp point because you have an unlimited number of lines that have a bunch of different slopes that are tangent to this point. So at sharp points, derivatives are not defined. So there is no velocity at that point. It's undefined. What this means is that this kind of motion does not reflect what happens in real life. What happens in real life, if you're going from 8 meters here up to 10 meters and then you're going back down, what happens in real life is that you're going to see a little curve because it takes a little bit amount of time to go back and forth. So if you did have a curve instead of a sharp point, and you wanted to find the instantaneous velocity at that point, the edge of the curve here, well, in that case, the tangent to this line would be a horizontal line, and the instantaneous velocity at that point would be 0 if you had a curve. But since we didn't have a curve, we had a sharp point, the velocity was undefined.